Lab 3 Black Hole in Orbits by Harsh Shah. Purpose of the lab. This lab involves doing computational physics to analyze and simulate circular motion. Part 1 involved analyzing circular motion of a star around a black hole to find out the black hole's mass. Part 2 involves simulating motion of a ship around the moon and trying to, in a star system, and trying to predict velocities that would induce a figure-8 orbit for the ship. Concepts used in this lab are Newton's second law, centripetal force, gravitation, kinematics, circular motion, and vector operations, and momentum change. Preview the results. In part 1, the equation of the universal law of gravitation was modified to isolate the mass of the black hole, and the other known information was used to find it. In part 2, through trial and error, the starting velocity of the ship is modified to try to induce it into a figure-8 orbit, which I couldn't do, but was still able to produce an orbit that showed gravitational effects of both the star and the moon on the ship. More info about the concepts used. The universal law of gravitation equals gm1 m2 over r squared. Newton's second law is F equals ma. Kinematics position update is Rfi equals Ri plus V delta t. Velocity update is Vf equals Vi F net over mass times delta t. And momentum change is dp over dt equals F. For the system and surroundings, in part 1, the system is the star and the surroundings are the black hole. And in part 2, the system is the spaceship. The surroundings are the moon and the star. When we're calculating the information about the spaceship, and when we're calculating the information about the moon, the system is the moon and the surroundings are the spaceship and the star. Procedure of part 1. First, the mass of the star is estimated. It doesn't really matter since it cancels out in our calculation. Delta t is calculated to be 24 hours times 60 minutes times 60 seconds. And the initial and final momentum is calculated and used to find change in momentum divided by the change in time, which is the F net on the star. F net is divided into its parallel and perpendicular components to be displayed in the simulation. And then the universal law of gravitation is used to obtain the mass of the black hole at each step of the while loop, and then all of them are averaged out to find the final mass. First, we find the initial momentum and final momentum of the star, which is v init times star dot m or and v final times star dot m. We find the delta p, which is p the final momentum minus initial momentum, and we divide that by delta t to find dp dt, which is also equal to F net. Then we get the direction of the momentum and dot product of the F net to find the parallel aspect of F net. And we also just use the formula like force parallel plus force perpendicular equals force to find the dp dt perpendicular, which is F net perpendicular. And then we use the gravitational law to find mass of the black hole by doing the magnitude of F net times magnitude, the star position squared divided by the mass of the star times the constant g, and then we average out the mass at each step to find the final average. These are the results. Part 1 conclusion. By using the law of gravitation and momentum change equation, we were able to isolate and find the mass of the black hole using the equation F net times magnitude of r squared divided by g times the mass of the star. And since it's a purely computational model, there should not be any human errors. Any deviation from an actual mass will be due to the model using approximation of F equals dp over dt, using average velocity change equation instead of instantaneous velocity, and averaging the final mass. Procedure of part 2. We first guess the initial and x and y velocity of the ship. In the while loop, we calculate the gravitational force on the moon from the star and the ship, and add them to find the net force on the moon. Then we calculate the gravitational force vector on the ship using the same process, and we use the second law of motion and kinematic equation to update the moon and the ship's velocity and position vectors. Then we do trial and error to find the velocity which makes the ship have an influence from the moon and the star. In the code for part 2, we initially estimate the x speed and the y speed, and then we use the kinematics equations and the second law to basically find the trajectory of the ship. Here are the results for part 2. Part 2 conclusion. This part was simulated using the law of universal gravitation applied to a three-body system model. It was discovered that the ship's resulting trajectory is extremely sensitive to the initial velocity, and obtaining the figure-8 orbit was not successful. However, an orbit which showed the effects of the gravitation from both moon and star on the ship was seen. Sources of error include the model being very simplified and the model being very sensitive to small changes, making the process of finding the values that would create the figure-8 orbit very difficult. Additional questions. What does it mean? Force equals dp dt, but force is the agent that can be measured, and dp dt is the effect that is observed. The parallel component of force leads to speeding up or slowing down the object, whereas the perpendicular component changes the direction of the object. What if question? If all the components were included, the gravitational force from the black hole would be the most dominant since it has the greatest mass. The dominance of each object's gravitational force will vary according to their mass. To simulate the trajectories, we would have to calculate the gravitational interactions of each pair of components and update their position and velocity accordingly. Thank you.